Hello everyone, welcome to another video on statistics, and in this video and a few more to come, I'm going to be dealing with statistical inference 1, STA 1502, and I'll be working on assignments from the 2023 academic year. So assignment 1 has 8 questions, and I will deal with only question 1 in the first video and question 2 in the second video, and so on, because it's a lot of information that we need to provide in each question. So question 1 here says, consider two independent random samples that were selected from two normal populations as given below. We have sample 1, sample 2, and we have been given sample sizes and also the mean and also population standard deviation. Once you have been given population standard deviation, it means we're going to use the z-test, right? So the researcher wants to test if the two population means differ at 5% level of significance. That word there, differ, basically means we have a two-tailed test here. I'll explain to you what a two-tailed test is. Here it says, which one of the following statements is incorrect? So being given 5 options or 5 statements, we are supposed to choose the incorrect one. And how I answer these questions is by going through the entire question as far as hypothesis testing is concerned, and then come back here and select which one would be the correct option. So let's look at the 6 steps then in hypothesis testing. I'm going to start by perhaps labeling this as STA 1502. Let's call this page 1. We're dealing with 2023. This is assignment 1. Let's look at question 1. And in hypothesis testing, we have 6 steps. Step 1, we have to state the null hypothesis and the alternative hypothesis. Now, in this case, the question says, the researcher wants to test if the two population means differ. That, like I told you, it doesn't tell us direction there, greater than or less than. It says whether the two populations differ or not. So basically, we're going to say in our null hypothesis, the two population means do not differ. So that means that mu1 minus mu2 is actually equal to 0. In the alternative hypothesis, we are going to say they actually differ. They are not the same, which means that this mu1 minus mu2, the answer is not equal to 0. Like I told you, this here shows no direction. It means we have a what we call two-tailed test. I'm going to explain to you what this means, right? So step 1 we are done. Let's move to step 2. And if you remember, in step 2, that's where we state the alpha level. So in this case, we have been told that the level of significance is 5%. And because we have a two-tailed test, we have to divide this by 2. So we're going to say this implies alpha over 2 is actually 5% over 2. And this is 2.5%. Now, what is 2.5%? This is actually 0.025. So that is the value of alpha over 2, and we divide that only when you have a two-tailed test. Right. Now, that is completed. Then we are now moving on to the third step. And in the third step, if you remember, this is where we compute what we call the critical value. Now, because we're using the z-test, we need to work out area on the left first, because the table I'm using in this case, the z-table I'm using is shaded on the left. And therefore, we are looking for area on the left of the critical value. So area on the left, remember, capital A sub L for area on the left is always 1 minus, in this case, alpha over 2. Sometimes it is alpha, but because we have a two-tailed test, it will be alpha over 2. So what is this? This is 1 minus 0.025, and your calculator is going to say 0.975, I believe. Let me just confirm on my calculator here. 1 minus 0.025, and the answer, yes, 0.975. So this is area on the left. and therefore there is a special critical value that corresponds to that area, which we're going to look up in the table. So we're going to say, therefore, our Z critical, we know the value of alpha over 2 is 0.025, which corresponds to that area. Let's check in the Z table. So we're looking for this number in the Z table, and it's 0.975. I'm gonna have to check the positive Z table that I have here. Let me just get it. The positive Z table, I have it somewhere. Just give me a minute. So many papers here. Yeah, I had it just a few minutes ago. Let me just check here. I should have it here. There you have it. The positive Z table, there it is. So I'm looking for the 0.975, and if you check on this table here, there is the number 0.975. So what critical value Z value corresponds to this value, this area on the left is 1.9, and then move up 6. So 1.96 would be the value of Z we're looking for, and because we have a two-tailed test, it will have to be plus or minus 1.96. So this is our Z value, 1.96, but like I said, because of the two-tailed test, we'll put plus or minus there. So the critical value has been obtained. Now we're moving on to step number 4, which basically is the calculation of the test statistic. Now on the test statistic, in step number 4, let's list down the data first. So step number 4, I'm going to have to list down the data because we've been given quite a lot of information here. Listing down the data, according to this question here, we have two samples, 1 and 2. So we have to list that information. Sample 1 and then sample 2. Let me call this page 2. We have N1, sample size 1. Sample size for sample 1 is actually 18. So this is 18. Sample size for sample 2 is 20, as you can see here. And then mean for sample 1 is 10, 20 for sample 2. So X bar 1 is actually 10. X bar 2 is actually 20. And then we've been given population, standard deviation of population 1. So this is sigma 1 is 2.1, as you can see here, 2.1. And then for the second one is 2.8. So 2.1, sigma 2, 2.8. Right now we can calculate the test statistic because we have the information, and then we have that the first parameter or quantity to work out is a test statistic. So Z stat, I normally put stat there to differentiate it from the critical value, but some books who don't actually indicate stat there. The formula says X bar 1 minus X bar 2, this minus the hypothesized difference mu1 minus mu2 all over the what we call standard error of the difference between the population, between the sample means. So that's going to be square root of, so we have sigma 1, we square it all over n1, plus sigma 2, we square it all over n2. Now, let's punch in the numbers then. Remember, mean of sample 1 is 10, you can see it here, minus mean of sample 2 is 20, minus the hypothesized difference is 0. Here it is, hypothesized difference. I told you this is critical because we need it in our calculation of the test statistic. So that will be 0 all over square root of 2.1 we square it because we're dealing with variance here, all over the sample size for sample 1 is 18 plus 2.8. We're squaring that, all over sample size is 20. Punching this into the calculator, what we get is, I like to punch the whole thing into a calculator. Some lecturers don't like to do that, so depending on what your lecturer likes, stick to what they like. 2.1, we're squaring this all over 18 plus 2.8, we square that all over 20. My calculator says minus 12.5294, minus 12.5294. Now, if you calculate, if your lecturer breaks this calculation down into the numerator and denominator, there might be a difference there on the last digit, right? It's due to rounding. All right, what else do I need to calculate? Remember, I told you that I would discuss everything around question 1. I also want to work out what we call the standard error, SE, of the difference between the sample means. Standard error, like I told you, this is going to be, in this case, sigma 1 squared over n1 plus sigma 2 squared over n2. Performing the substitution, this is what we get. 2.1, we square it over 18, sample size for sample 1. 2.8, we square it over 20. And then our calculation produces 2.1, we square that all over 18, and then plus 2.8, we square that all over 20. My calculator says 0.7981, 0.7981. That is the standard error of the difference between the two sample means. I also want to work out what is known as the error bound for the mean, so EBM. We need that when you are busy or you want to determine or calculate what we call the confidence interval. So I'm going to do that calculation. It may not be required in this question, but in an exam they may actually require that information. So I want to explain how we do it. So the next item I want to look at, like I said, EBM, error bound for the mean. The formula says, like in this case, we're dealing with z-test, so it's going to be z alpha over 2, because it's a two-tail test, times the standard error of the difference between the two sample means. So this has been calculated, but we need to work out, and in fact this has also been determined already. If you remember, z alpha over 2 is 1.96. Here it is, z alpha over 2, which is that value there, that's alpha over 2. You can see it here. It's actually 1.96, so we have both numbers. This is 1.96. We take the positive value only, times this part, which is 0.7981, and this gives us 1.96 times 0.7981. My calculator says 1.5643. 1.5643. That's EBM, error bound for the mean. That's what it is. Now, I want to also determine the confidence interval here. Remember, the alpha level is 5%. So therefore, this is the level of significance is 5%, and therefore the level of confidence will be 100% minus 5%, which is 95%. So we are now saying next item is 95% confidence interval CI of the difference between the two population means is equal to the sample mean of sample 1 minus sample mean of sample 2 plus or minus EBM. That's why we needed to calculate that. EBM. So let's do the substitution now. This one, remember, is 10 minus that one is 20. You say, where is that information? Here it is. That's x bar 1 or x1 bar 10. Sample mean of sample 2 is 20. So we're going to say plus or minus EBM is 1.5643. Let's perform the calculation here. We have, obviously, this is minus 10. And then we're saying plus or minus 1.5643. So I'm going to say, let me just punch all the information here. It's minus 10 and then minus 1.5643. My calculator says the lower bound is minus 11, and I'm going to round off to 3 decimal places just for accuracy purposes. Minus 11.564, 564, comma. The upper bound is going to be, we're changing the minus sign to plus sign there, to plus sign, and it says minus 8.4357. So it's minus 8.436 to 3 decimal places. So that is 95% confidence interval. We are basically saying that the difference between population means is less than this value here, which is minus 8.436, but it's greater than this number, which is minus 11.564. So we are basically saying we are 95% confident that the difference between the population means of the two populations is between this number here and that number there. Right. Now let's move on, because this is the information, additional information I thought I should explain how you determine. Let's move on to step number 5. And step number 5, if you remember, in step number 5, that's where we determine, we make a decision. It's a decision rule step. Step 5, decision rule. What is the decision rule? It says reject the narrow hypothesis if the test statistic is less than the negative value or greater than the positive value of our critical value. So in this case, we're going to say z stat, we're going to say we ignore or reject H naught if z stat is actually greater than z crit, if you're considering the positive value of that, and this is the same as z stat is less than the negative value of this. So if you take 1.96 here it will be less than minus 1.96. So we're looking at the two conditions there. Remember, I told you that z crit has two values. It's positive, plus or minus there. So now let's sketch our normal distribution curve then. So this is basically what I'm saying. And we know that in the center there we have 0, and 1.96 is somewhere here, 1.96, and by symmetry, like I told you, 1.96 is going to be minus 1.96 will be somewhere here. This is the rejection region. What is area there? Shaded area, it's alpha over 2, and we say this is 0.025. This shaded area here also is alpha over 2, which is 0.025. The central part there is 95%. Now let's compare our test statistic and these two critical values. If you check the test statistic here, is minus 12.5294. Is way to the left side there. That's where you have minus 12.5294. It falls in the rejection region. So we're going to say, therefore, we reject HO. And I want to say something very special here. We reject HO because the test statistic falls in the rejection region. But there's also something very nice for you to notice. We've determined the confidence interval. Basically, if we reject HO, we're basically saying that the difference, hypothesized difference, is not in that interval. And you can clearly see that we hypothesized that the difference between the two is 0, and 0 is not a number in that interval. It's outside of that interval, because remember, these are both numbers to the left-hand side of 0 on the real number line. So the confidence interval also can be used to test the given condition, whether the difference between the two means is 0 or not. So we can use the traditional approach, which is by using the normal distribution and comparing the test statistic and the critical values, or we can use the confidence interval. And the third way of comparing or determining whether the population means are the same or not is by using what we call the p-value. And I want to do the calculation of p-value here now. P-value for a two-tail test, remember, it's twice the probability that the z-value lies to the left-hand side of this number here, which is minus 12.5294 times 2, because we have two tails there. So this is going to be 2 times, let's determine that probability from the negative z table. So the negative z table, why negative? Because that number is negative there. Minus 12.5294 is negative. So we're coming here and we're looking on the left side here. If you check, the biggest number you have there is, it says here, minus 3.5, and lower, it's 0.001. So smaller than this number here, obviously, is going to be 0, because minus 12 is very far away from minus 3.5. So our value, our p-value for z less than that is going to be 0.000024 decimal places. Multiply by 2, you get the same number, 0.000. That is the p-value. So we've done all the necessary calculations that are required in hypothesis testing. And now we must go back to the question and check, because the question requires us to check which of the options provided is incorrect. So let me number these pages. This is my page 3. Page 1 is this one, page 2, my page 3, and my page 4 is this one here. This is page 4. So we have all the pages. Remember, step number 6 is a conclusion step. We have to state whether we have enough or sufficient statistical evidence to reject the null hypothesis or reject the alternative hypothesis. Remember, we said there are 6 steps here. If we can call this step 1, that would be step 2, that would be step number 3. In step 3, that's where we determine, like I told you earlier on, the critical value. There it is. In step 4, we determine the test statistic. This is step 4. And step 5, decision rule step. Remember, here I said there are a couple of more information we need to determine, and which I have done. This is step 5, the decision rule step. And step 6 is the conclusion step. Now, in this case, it's not necessary, because the researcher just wants to determine whether there's a difference or not. So there is no specific claim here, so we don't have to worry about step number 6. But let's look at the question then. Let's look at the question. Question 1, what does it say? We have to determine, let me check the page. I have too much paper with me here. There is a question. Which of the following is incorrect? Which of the following statements is incorrect? Right. Null hypothesis, mu1 minus mu2 equals 0. Let's go to page 1. Where is my page 1? Oh, here it is. So you can see that one is actually correct. So this statement here is correct because we're looking for the incorrect one, and that is correct. Standard error of the difference between two sample means, 0.798. What did we find in our calculation there? On page 2, 0.7981. I told you the last digit there would be different because of rounding, and in this case, they rounded off the answer to 3 decimal places, I think, for accuracy purposes. So it's 0.798, 0.7981. So this is also correct. We're looking for the incorrect option, remember? And then we're moving on to statement number 3. The critical value at 5% level of significance is 1.96. Of course, we determined that in step number 3. Step number 3, there is the critical value. The plus or minus is because of symmetry, like I explained, but 1.96 is the correct value. So that one is also correct. The test statistic is minus 12.5298. I told you the difference would be because of rounding. Here I didn't round off, so this is the more correct answer than this one, because this is obtained by determining that and rounding and then dividing into the numerator there. But if you punch all that information into your calculator, this is what it gives you to 4 decimal places. So this one is also correct. This is the incorrect one. The p-value 0.5 is not correct, because according to our calculation, the p-value is actually supposed to be, here it is, 0. That is the p-value 0. So the correct answer, which is the incorrect option according to this question, is the last one there. All right, I'm going to stop here in this video. When I come back with my second video, I'll be dealing with question number 2, and we'll move on up to question number 8, then move to assignment 2, assignment 3, up to assignment 4. By the time I finish going through all these 4 assignments, you should have the confidence to be able to write STA 1502, which is statistical inference, and that's first year statistics, those of you that are doing first year statistics. All right, I'll stop here. If you are new to the channel, please support us by subscribing, inviting friends to subscribe, liking these videos and sharing them. It will enable us to produce many more videos and support as many students as possible. If you need one-on-one lessons, please hit me up in the comments section, and then we can make necessary arrangements for online lessons. All right, see you next time.